Imagine one of our distant ancestors moving cautiously through the grasslands, tracking prey while trying not to become prey themselves. In that unforgiving world, a second heart sounds like the perfect backup. If one failed, the other could keep beating. Yet evolution gave us 2 lungs, 2 kidneys, and 2 eyes, but only 1 heart. So why didn't natural selection give us another? The tempting answer is that evolution made a bad design choice. But evolution never works from a blueprint. It changes what exists, one workable variation at a time. Each step along the path must function well enough to survive. A feature remains only when its benefits outweigh its costs, including the intermediate steps needed to build it. That makes a second heart harder to evolve than it first appears. Saying humans have only 1 pump is also misleading. The organ we call the heart is really 2 pumps fused into one coordinated machine. Its right side receives oxygen-poor blood and sends it toward the lungs. Its left side receives oxygen-rich blood and drives it through the body. Both sides contract during every normal heartbeat. 2 workloads, 2 pressure systems, 1 tightly synchronized organ. That arrangement matters because our circulation has 2 linked loops. The pulmonary circuit is short and low pressure, protecting delicate vessels around the lungs. The systemic circuit is long and high pressure, pushing blood from the brain to the toes. A mismatch would quickly flood one circuit or starve the other. Combining both pumps inside one structure lets every beat move the same volume through each loop and keeps the system balanced. Our paired organs are not spare copies waiting for disaster. Usually, being paired helps perform their ordinary job. 2 lungs provide a huge exchange surface around the heart. 2 eyes view the world from different angles. 2 kidneys filter blood from opposite sides. Each pair earns its place differently. Their duplication serves geometry, capacity, and development, not merely emergency backup. Take the lungs. You can survive with one, but your body normally uses both with every breath. They divide the chest efficiently and provide enough exchange surface for exercise. Both lungs are working tissue from the very first breath. Losing one leaves less reserve. It does not reveal that the other was sitting idle. The pair is one distributed respiratory system, not a primary lung and a spare. The kidneys come closer to genuine redundancy. A healthy person can live with one because each has more filtering capacity than daily life demands. Still, both are active, share the workload, and arise from the embryo's left-right organization. Their small repeating filtration units are easy to scale and distribute. That modular structure makes partial loss surprisingly survivable. A high-pressure muscular pump is a different problem. Our eyes illustrate another reason evolution repeats structures. Their separation lets the brain compare 2 images and estimate depth. A single central eye could still see, but it would lose much of that binocular information. The second viewpoint is useful every moment the eyes are open. Here, duplication creates a new capability. 2 hearts pushing into the same vessels would not create a cleaner picture. They could create interference. Suppose evolution placed 2 full-size hearts in parallel, both pumping into the same arteries. Their pressure and timing would need to match closely. The same blood connects both pumps, so neither is truly independent. If one contracted earlier or more forcefully, it could push against the other, reverse flow through shared vessels, or leave one pump doing most of the work. Redundancy would become a coordination problem. Engineers solve parallel pump problems with valves, sensors, controllers, and tuned plumbing. Biology can evolve these, but none is free. A second heart needs extra vessels, nerves, valves, tissue, and chest space. It consumes oxygen and calories while creating more places for clots, infections, rhythm problems, or defects. The hearts would also have to agree on tempo. Even one heart contains billions of cells whose contractions must spread in an orderly wave. Pacemaker tissue starts the signal, conduction pathways distribute it, and timed valves direct the blood. Another independent organ means linking 2 electrical systems across distance. Lost synchronization could turn 2 healthy pumps into one unstable circulation. What if the second heart were placed in series, so blood passed through one and then the other? We already use that principle inside the fused heart. The right pump serves the lungs, then the left serves the body. Another full systemic pump would mostly raise pressure or duplicate completed work. Downstream vessels would need reinforcement, costing more material and energy. Development makes duplication harder still. Early in a vertebrate embryo, cardiac cells form a tube near the midline. It bends, loops, partitions, and connects to growing vessels, eventually producing 4 chambers. Every stage depends on signals arriving at the right place and time. Copying the process could disrupt the entire circulation before birth. Evolution modifies this inherited pathway rather than rebuilding it. Vertebrate hearts vary in chamber number, separation, and flow, yet remain versions of the same ancient pump. Fish use a 2-chambered sequence. Amphibians and many reptiles separate flows less completely. Birds and mammals evolved 4 chambers. Natural selection improved the original layout instead of installing another systemic heart. But multiple hearts are possible. An octopus has 3. 2 branchial hearts push blood through the gills, while 1 systemic heart sends oxygenated blood around the body. This works because the pumps have distinct jobs and circuits. They are not identical backups, but specialized stations in a circulation shaped by different anatomy, blood chemistry, and respiratory demands. Other animals stretch the definition further. Earthworms have muscular aortic arches that move blood, although calling them 5 human-like hearts is misleading. Hagfish possess a main heart plus accessory pumps assisting different regions. In each case, multiple pumping structures solve a specific flow problem. Evolution can build extra pumps when specialization is worth the added machinery. Our ancestors inherited another solution: make 1 central heart remarkably capable. At rest, it works below maximum output. During exercise, it beats faster and ejects more blood with each contraction. Training can improve efficiency, while hormonal and nervous signals adjust performance from moment to moment. Instead of carrying a dormant replacement, the body keeps reserve capacity inside its existing pump. The heart also has limited functional backups. If its primary pacemaker fails, slower pacemaker regions can sometimes sustain a rhythm. Collateral vessels may provide alternate routes around narrowing arteries in some people. 4 chambers and one-way valves keep blood moving efficiently. None of this makes the heart failure-proof, but redundancy can exist inside a system without duplicating the organ. There is a deeper issue. A backup matters only if it improves reproductive success often enough to spread. Many forms of heart disease become common late in life, after ancestors had raised children. Selection can still act through survival and family support, but its pressure is weaker. A second heart carried from birth may offer little advantage against problems appearing decades later. Many ancient threats would defeat both hearts at once. Severe bleeding empties the same circulation. Starvation deprives both pumps of fuel. Infection, venom, overheating, or suffocation changes the blood reaching both organs. Predators and major injuries damage several systems at once. A second heart protects against a narrow set of failures while charging its cost every day. Perhaps the backup could remain switched off until needed, but living tissue cannot wait like an unused engine. It needs blood, maintenance, electrical control, and protection from clotting. Muscles that never work can weaken, while valves and vessels deteriorate under abnormal flow. Keeping the heart active avoids those problems, but returns us to the cost and synchronization problems of 2 pumps. Modern medicine shows the promise and difficulty of extra pumping power. A ventricular assist device can help a failing heart, and an artificial heart can replace major pumping functions. These machines save lives, yet require power, monitoring, surgery, and careful management of bleeding, infection, and clotting. Adding a pump is possible. Integrating it safely is difficult. Even transplantation does not create simple redundancy. Surgeons usually replace the failing heart rather than leave 2 complete organs sharing 1 job. In rare operations, a donor heart has been connected alongside the original, but pressure and plumbing require careful management. Medicine accepts complexity for a patient in danger. Evolution weighs it across every healthy member of countless generations. The real comparison is not 1 heart versus 2 in an imaginary perfect body. It is our integrated heart versus every viable intermediate needed to evolve and maintain another. 1 heart is compact, synchronized, developmentally established, and powerful enough to provide substantial reserve. A second could help in certain failures, but would introduce costs and vulnerabilities long before they occurred. Evolution did not leave us with a half-finished design. It turned an ancestral heart tube into a 4-chambered organ containing 2 coordinated pumps, plus reserve capacity and limited internal backups. Other animals evolved more pumps when their circulation required specialized jobs. For humans, one integrated double pump was the better bargain. The mystery is not why we lack two hearts. It is how much work one already does.